Well, we are going to continue now with our discussion of ring compounds from Chapter 5. And so far, we've covered quite a bit of territory. Without trying to be exhaustive, we have seen, for example, how to draw cyclohexane in a chair form. By by using the words chair form, I mean in a conformation which is described as a chair form. We know that cyclohexane, like all organic compounds, can adopt many different conformations. The chair form just happens to be the lowest energy conformation for cyclohexane. It's the one that allows us to call cyclohexane an essentially strain-free molecule. In addition to looking at regular old unsubstituted cyclohexane, we also studied last time mono-substituted cyclohexanes. So we've looked at cyclohexane itself and mono-substituted cyclohexanes, and we looked at a couple different ones, I believe. We even looked at di-substituted. Cyclohexane. So if you go back in your notes, you're going to see examples of all of those. And when I say we went over them, that includes the fact that we drew them in their proper chair forms, showing all axial and equatorial bonds. And we also talked about the fact that when you ring flip, these compounds, we notice that the axial positions interconvert with equatorial. So ring flipping promotes interconversion of axial and equatorial, and it's a completely dynamic process. Ring flipping can go back and forth. So groups that are drawn initially in an axial conformation can very easily become equatorial just by virtue of ring flipping. And then whether or not the equatorial form is more stable, it doesn't matter. They'll continue to ring flip back and forth. So each group is going to spend some time in axial, some time in equatorial, and it's a completely dynamic process. We also talked about the fact that if the group is up, it continues to be up after ring flipping, and if the group is down, it continues to be down after ring flipping. So ring flipping interconverts axial and equatorial, but does not change the up-down nature of the substituents. We did a couple of other things, like, for example, draw double Newman projections, and talked about stereochemistry. And I want to just emphasize on the stereochemical front that whenever there are stereochemical questions, you are much better off looking, for example, at the flat or two-dimensional cyclohexane drawing like this one. So this molecule right here happens to be cis 1,3 dichloro cyclohexane. If you look carefully, there are two stereogenic centers there and there. This particular molecule happens to be meso. There's a plane of symmetry which rips through the middle of the molecule. One side is identical to the other, so this is a mirror plane. But it is a meso compound, and so a better term than cis here would actually be meso. Meso 1,3-dichlorocyclohexane. If we determine the RS absolute configuration at each of these stereogenic centers, which is something we know how to do, it is better to do that with this two-dimensional drawing of this cyclohexane rather than looking at a chair form. It can be done looking at a chair form, it's just much more difficult. So from here we go to chlorine, to the carbon that is closer to the second chlorine, to the carbon that is further away. We see that this is a clockwise rotation with the group of lowest priority, this hydrogen atom, which wasn't drawn until now, in the back. That is an R absolute configuration. Over here, from this chlorine to the carbon that's closer to the chlorine to the carbon of the ring that's further away, we get a counterclockwise rotation. This is clearly S. So this is the RS, or meso 1,3-dichlorocyclohexane. That name really indicates exactly what molecule we're talking about. rather than one of the other stereoisomers that exists for 1,3-dichlorocyclohexane. So let's go ahead and draw this 1,3-dichlorocyclohexane in its chair forms. Now last time I believe we looked at 1,2-disubstituted compounds, including 1,2-dibromo and maybe 1,2-dichlorocyclohexane. This might be the first time we've looked at a 1,3 disubstituted cyclohexane. So what we've got to do is we've got to draw our cyclohexane initially. And it doesn't really matter where you start counting. There's nothing special about calling this particular carbon, which I refer to as the nose-up carbon, carbon 1. It's perfectly okay to use it as carbon 1 in every example, but it's also okay to start counting here or here or here or here or here at any of those carbons. It may not look like it, but this chair form of cyclohexane has 6 identical carbon atoms. And if we could lift this off the paper and examine it in 3 dimensions and twist it around, we would see that all of the carbons are exactly equal to each other. So it really is completely arbitrary with regards to where we start counting. But I like to start up here at the nose-up carbon, call that carbon 1, and you can see that in my 2-dimensional drawing the chlorines are both up. So we're going to put the first chlorine in an axial up position, because we know that the axial position is straight up off of the nose-up carbon. There's an equatorial hydrogen right there. And then we come down to carbon 3 and we see that the chlorine is also up at carbon 3. So it's got to be axial up in this case. The equatorial hydrogen must be on a bond that is parallel to these carbon-carbon bonds, which are 1 bond removed. So again, 1, 3, just like this was 1, 2, 3, 4, 5, 6. I'm just following the 2-dimensional drawing, and in particular I'm following the fact that the chlorines are both up. The fact that those chlorines are up says nothing about whether they're axial or equatorial in this chair form. There's no relationship whatsoever. But we do have to maintain this cis stereochemistry. The 2 chlorines need to be cis, and since they're on 1,3 carbons, and since I drew the first one in an axial position, I know that the chlorine on carbon 3 must also be axial, because that's the other up position. Now looking at this 1,3-dichlorocyclohexane, we can see that there are some syn-diaxial interactions here. We've got 2 non-hydrogen groups, these 2 chlorine atoms plus 1 hydrogen atom, all occupying this axial space on top of the ring. So this is a little bit more severe than some of the other syn-diaxial interactions we've seen. Chlorine's not the biggest atom in the world, so it's not horrific by any stretch of the imagination, but it's a little bit more significant than, for example, if we just had 1 chlorine atom in an axial position. Well, we know that we can ring flip, and when we do that, we're going to drag that nose-up carbon down and push that nose-down carbon up. Carbons 5, 6 and 2, 3 are going to slide past each other. So let me go ahead and do that. There I've slid 5, 6 over and 2, 3 over in this direction. This nose-up carbon is coming down. So for example, right there. And then we just need to fill in the missing pieces. This now becomes carbon atom 1. There it is. Nose up has slid down. 2 and 3 have slid over. 2, 3, 4, 5, and 6. Well, since I started with an axial up chlorine at carbon 1, I know that it now must be equatorial up. Notice that that hydrogen was equatorial, and now it's axial, just as the chlorine started axial and is now equatorial. But the up nature of the 2 chlorines hasn't changed, and neither has the down nature of the 2 hydrogens. Now I move over to carbon 3. It was axial up, I should say the chlorine at carbon 3 was axial up, so now it's going to be equatorial up. If you have a hard time keeping track of where these axial and equatorial bonds should be, Remember, the axials are always straight up or straight down, and they alternate. So this axial hydrogen on the nose down carbon is down. At carbon 2, if I drew it in, it would be up. And then the axial position here would be down at carbon 3. This is actually going to be where the hydrogen is. You can see the hydrogen at carbon 3 in this chair form started out equatorial down. Now it will be axial down. The chlorine started out axial up. So now it's going to be equatorial up. Whoops, that's a chlorine, not a hydrogen. Of these two forms, these two chair forms, you can see that my largest groups, the non-hydrogen chlorines, are both axial in the first chair form I drew, and there are those syn-diaxial interactions which destabilize the molecule to some extent. Moving over here to the second chair form, my largest groups, my non-hydrogen groups, are all in equatorial spots, and so this is clearly better. This is the most stable, lowest energy chair form for this particular molecule. So that's the way we do these analyses. They're all quite similar, actually. We've looked at 1,2 examples, 1,2 disubstituted cyclohexanes in class. Here's a 1,3 example. Let's go to a 1,4 example. This is going to be an interesting one. We're going to look at a 1,4 dibromo. Let's put our bromines, we could either make them cis or trans. I think we'll make them trans. So there's my flat two-dimensional cyclohexane. Remember, this is always a good place to start, especially if part of the problem involves assigning stereochemical R and S configurations. In this particular case, although we might at first glance think that this is a stereogenic center and that's a stereogenic center, it turns out neither is, because thinking about this carbon here, this collection of atoms and groups is identical to that collection of atoms and groups. That is, moving around the ring in a clockwise fashion, I encounter exactly the same things in exactly the same times as when I move in a counterclockwise direction. And the same is true here. So essentially this carbon is bound to two of the same exact atoms or groups, and so is that carbon. So neither one is a stereogenic center. And I don't have to worry about stereogenic centers here or stereochemistry other than the fact that this is trans. If we're going to properly name this compound, it would be a 1,4 dibromo cyclohexane, but I need to specify that it's not the cis stereoisomer, it's the trans stereoisomer. So trans 1,4 dibromo cyclohexane. All right, well, let's go ahead and draw trans 1,4 dibromo cyclohexane in its most stable chair form. So we're going to start with a chair form. There's my 6 carbons in a chair formation, and I'm going to go ahead and call this carbon 1, 2, 3, 4, 5, and 6. And notice that I've got my bromine up, so I'm going to be consistent here and show my bromine is up in an axial spot. The down position is the equatorial position, parallel to those two bonds. This one should be. Over here at carbon 4, since this bromine is up, this one is down. This bromine is axial up. It must be axial down here. And again, if you have any confusion about that, just remember that the axial positions are straight up and straight down, and they alternate. So straight up, straight down, straight up, straight down. So the two axial positions on 1,4 are sort of naturally set up to be trans. And then I want to go ahead, put my equatorial hydrogen in. So I just happen to have drawn this molecule in a chair form in which both bromines are axial. Now, both bromines will have sets of syn-diaxial interactions involving the bromine and the other axial hydrogens on their respective faces. Unlike the last example, in which the chlorines were both occupying the same diaxial syn space. Here, the bromines are on opposite faces. This bromine is on the top face, this bromine is on the bottom face. They have unique sets of syn diaxial interactions, this bromine with these two hydrogens and this bromine with those two hydrogens. Turns out, energetically speaking, they're not so unique, they're pretty much the same, but they're unique faces. The bromines are on unique faces, and so there's two sets of syn diaxial interactions. Well, if we ring flip this compound, we will see that those syn diaxial interactions will go away. And we can predict that even before we draw it. Think about why that is. That's because the bromines, which are both axial, will convert to equatorial positions upon ring flipping. This one will be equatorial up, this one will be equatorial down, but they'll both be equatorial. And we know that for our larger non-hydrogen substituents, it's going to be energetically preferred to place them in equatorial positions. So let's go ahead and draw our ring-flipped molecules. And that's the nose-up carbon here, which is now nose down. 2 and 3, carbons 2 and 3 have been slid. 5 and 6 have been slid in the opposite direction, such that I have this parallel displaced arrangement. Well, bromine was axial up at carbon 1, now it's going to be equatorial up, and the axial position will be occupied by this hydrogen. Over here at carbon 4, bromine was axial down, now it's going to be equatorial down. And once again, the hydrogen, which was formerly equatorial, will now be axial and will occupy the axial position. Of the two, this is clearly the most stable, lowest energy conformation, because my two large groups are equatorial. So that's another couple of examples of how we deal with di-substituted cyclohexanes and how we decide whether or not one is preferred. Now sometimes, we saw an example like this in class, sometimes when you draw your two chair forms, you realize that energetically they are identical to one another. In other words, if you had one in an axial position and the other in an equatorial position, upon ring flipping, the one that was axial would go equatorial and vice versa. You'd still have one axial and one equatorial, they'd be identical. Look in your notes and you'll see an example like that. The last type of problem that we want to look at involves di-substituted compounds in which the two groups are not identical to each other. So for example, let's go ahead and look at a case in which we have a methyl group at this carbon and at the 3 position an isopropyl group. Notice that I've drawn them in a trans arrangement, but as we know, these are stereogenic centers, and if you look carefully, there's no plane of symmetry here, so there's actually going to be 2 versions of this stereoisomer, the one that I've drawn on the paper here, and its non-superimposable mirror image. In other words, this compound's chiral, and so it must exist as a pair of enantiomers. I've got one of those enantiomers shown right here. I want to name this particular enantiomer, not the other one, this one. So how do I do that? I need to go and look carefully at these 2 stereogenic centers. I've got to rank the substituents. Hydrogen will be the lowest ranked, and it's in the back, and I'm not going to draw it. This path around the ring here, closest to the isopropyl group, is going to be this path, which is further away from the isopropyl, and the methyl group will come in third. So we're going to go here to here to here. That's a clockwise rotation, which is R, as long as the group of lowest priority is in the back, and it is. Now we'll move over to this carbon here with the isopropyl, and we got to think carefully about this one. Let's work out carbon, which is bound to one other carbon, carbon, which is bound to one other carbon, And the carbon of the isopropyl, which is bound to two other carbons, it's a more highly substituted carbon, so it wins. So the isopropyl group will be the highest ranked group here, followed by the carbon that's closer to the methyl, closer to the more highly substituted carbon, followed finally by the carbon or the path around the ring, which involves more carbons before you get to the more highly substituted carbon. So it's going to go from here to there to there. That is a counterclockwise rotation, which is normally S, but because the group of lowest priority, not shown, is pointing out at us, hydrogen, instead of being S, we flip it to R. So this is the RR disubstituted compound. Now, question is, are we going to place this substituent or this substituent with carbon atom number 1? This is a tricky one. This is not a dimethyl. This is an isopropyl. And so we're going to count the I of the isopropyl, alphabetically speaking. The I of the isopropyl comes before the M of the methyl. So that's the only reason that the isopropyl group is going to get carbon atom number 1. They're both alkyl groups, so otherwise this would be a tie in terms of numbering. But because the I comes first, we're going to give the isopropyl group carbon number 1 instead of the other way around. So this is going to be a 1R, 3R. That sets the stereochemistry and tells us that we're talking about this particular compound and no other stereoisomer. The 1R, 3R, 1 isopropyl, 3 methyl cyclohexane. The 1R, 3R, 1 isopropyl, 3 methyl cyclohexane. There's the name. Now our job is going to be to draw this compound in its two chair forms and decide which of those chair forms is most stable and which is least stable. This one's going to be a little bit different than others we've seen. Let's give it a shot. There's my chair. Now, notice that in this particular drawing, carbon 1 is down here. We could continue to keep that there, or we could move carbon 1 up here. It really doesn't matter. As I've been saying over and over again, all 6 of these carbons on the cyclohexane are identical to each other, at least initially, before we add substituents. And so it really doesn't matter where you start numbering. I think that since I started numbering carbon atom number 1 right there, I'm going to try to be consistent, and I'm going to number the same way up here. Okay? Well, if you look carefully at carbon atom number 1, the isopropyl group is down in my chair form. A hydrogen would be up in an axial position, and down would be my isopropyl group. I want this bond to be parallel to this one, and also that one. If I move over to carbon atom number 3, the methyl group is up, not down, and at this particular carbon, it's an axial position that is up, so I put my methyl in axial up, and the hydrogen is equatorial down. So this looks like a pretty good conformation. I've got my methyl and my isopropyl group both, oh, I take it back. What am I talking about? This methyl is axial. The isopropyl is equatorial. So what does it mean? It means that the methyl group is going to experience some syn-diaxial interactions with those other 2 axial groups, happen to be hydrogen atoms, which are trying to occupy that same axial space. But my isopropyl group is equatorial, pointed, radiating away from the molecule, not bumping into anything. All right, let's go ahead and ring flip this. When I ring flip, of course, my nose up carbon's coming down, my nose down carbon's going up, carbons 4 and 5 are going to slide this way, and carbons 1 and 2 are going to slide that way. I like to start with these carbons that have just slid past each other, try to draw them parallel, and now we can add the nose down and the nose up carbon. Those bonds should be parallel, and if we've done things reasonably well, those last 2 bonds will also be parallel. Keep track now. The nose up carbon was 3 here, so it's going to be still 3 in the nose down position after I pull it down. And then it goes 2, 1, 6, 5, 4. Okay, well, methyl was, in this other chair form, axial up, so now it will be equatorial up, and the hydrogen moves from equatorial down to axial down. Over here at carbon 1, my isopropyl group was equatorial down. Now it will be axial down, and the hydrogen, which was axial up, will now be equatorial up. So what have I done? I've essentially swapped my equatorial groups. The isopropyl was equatorial in this chair form, the methyl axial. Now the isopropyl is axial and the methyl is equatorial. I need to consider syn-diaxial interactions for this isopropyl group. And there they are. Which one of these two chair forms is most stable and which is least stable? In a case like this, where we have two different substituents, what we really have to consider is which of the two substituents is the largest. Clearly, the isopropyl group with 3 carbons is considerably larger than the methyl group. Consequently, the syn-diaxial interactions involving the isopropyl will be more severe. Because the methyl group is smaller, these syn-diaxial interactions will be less severe than those. So of these two, this one is the most stable chair form, which means lowest energy. So that's a little bit different than what we've seen before. When we've got two groups, we've got to consider them both carefully. Well, it's not all that difficult though. I think if you just think about which groups are largest, you want to make sure that your largest groups are equatorial. That conformation in which your largest groups are equatorial is always going to be the lowest energy conformation. And the last thing I want to say before we leave this topic is that, once again, even though we've got a fairly large group here, this isopropyl, this molecule is not stuck in this particular chair form in which the isopropyl group, the largest group, is equatorial. It is true that that's a lower energy conformation than that one, but this is still a very dynamic process. The molecule ring flips back and forth quite rapidly, especially at room temperature. And so the molecule has access to these conformations and actually many others, which are not chair forms and are of higher energy. But of the two chair form conformations, it has certainly got access to both of those. And it just so happens this one is going to be a little bit lower in energy. So the molecule will spend more time in this conformation than it does in others. But all the other conformations are also accessible. That's a really important point. Okay, well, we've covered a lot of ground. We've talked about cyclohexanes with mono substituents and di-substituents, all different kinds of di-substituted cases, including two of the same group, 2 methyls, 2 bromines, 2 chlorines, and now we've seen a case where one group is different than the other, 1 methyl and 1 isopropyl. That's pretty much everything we need to cover with regards to cyclohexanes at this time. We will continue to see 6-membered rings, cyclohexanes and cyclohexenes throughout organic chemistry. But right now we're ready to move on to a slightly different topic. We are still in the same chapter, chapter 5, and we're still talking about ring compounds, but now we're going to introduce a new type of ring compound, namely bicyclics. These are ring compounds in which there are 2 rings in the same molecule. There are actually 3 different types of bicyclics. One is the so-called spirocyclics. Another is the so-called fused bicyclics. And a third are the so-called bridged bicyclics. So we're going to look at examples of all 3 types of bicyclic compounds. let's start with the spirocyclics. The spirocyclics share one carbon atom. In other words, we have two rings. Let's say one is a cyclopropane and the other is a cyclopropane. Yet they share this one single atom. This would be an example of a spirocyclic compound, and it looks a bit like a bow tie. It's possible to have many different types of spirocyclics. We could have a 5-membered ring, which is fused to another 5-membered ring in which they share one carbon atom. We could also have a 6-membered ring, which we know would prefer to exist in something close to a chair form, sharing, there's my axial, there's my equatorial bond, sharing this one carbon atom with a 5-membered ring. All of these are examples of spirocyclic compounds, spirocyclic bicyclic compounds, in which there are two rings, hence the term bicyclic, and they share one carbon atom. Spirocyclics are really interesting, and there are actually lots of natural products, molecules that are made in nature by various organisms, which are spirocyclic. They're very fascinating compounds. Another type are the so-called fused bicyclics. And here, the rings that are fused together share two carbon atoms. So, for example, what if we had a 6-membered ring fused to a 3-membered ring? You can see that the two carbon atoms that are shared by both rings are these two right here. We refer to those as the bridgehead carbons. The bridgehead carbons are the carbons, both of them, which are common to both rings. So that's a 6-membered ring and a 3-membered ring fused together, and two carbon atoms are shared, the so-called bridgehead carbons. There's lots of other bridgehead carbons in fused bicyclic compounds. For example, this is an aromatic compound called benzene, and we can fuse it to another 6-membered ring with all sp2 hybridized carbons, and now these two carbon atoms right here are also bridgehead carbons, and they're common to both rings. Now, interestingly, you can also do the same with 6-membered rings in which there are no pi bonds present. But let's look at this one carefully. Here we have essentially two cyclohexanes that are fused together. How is it different from these two benzene rings which are fused together? Well, these are all sp2 carbons and they're trigonal planar, so these carbons all lie flat in a plane. But these are all sp3 hybridized carbons, more three-dimensional. They do not lie flat in a plane. And in fact, it is possible for these junctions here to either be cis or trans. These compounds in which we have two 6-membered rings fused together are called decalin. That's a trivial or historic name. It's not an IUPAC name, although IUPAC recognizes it. We refer to this as cis decalin, and this would be trans decalin. Now, before we go any further, we really need to look more carefully at this cis and trans decalin example, because these are 6-membered rings, and we just learned how to draw 6-membered rings in their proper chair form. So let's go ahead and draw a 6-membered ring in its chair form. And now we want to go ahead and we'll start with this cis decalin. We want to make a cis decalin in which the bonds to the next ring, the one it happens to be fused to, are cis with respect to each other. Let's think about that. At this position over here, we could have an axial bond to a carbon atom. That's axial up. Over here, axial is down, so it would have to go to an equatorial bond. So there's my equatorial bond to a carbon, and there's my axial bond to a carbon. And I can just simply finish the drawing by showing the second cyclohexane fused in a cis fashion. This is cis decalin, equivalent to the first drawing I gave you, which looks like that. Very interesting. What about transdecalin? There's my cyclohexane drawn in a chair form. If I want trans, one of the bonds to a carbon has to be up. I'm going to show it equatorial up, and the other has to be down. I'm going to show it equatorial down. You can see that the axial bonds to hydrogen would be up here and down there. These are bonds to carbon over here. And in order to complete the story, all I have to do is finish the second ring. This is up, down. This is trans decalin, equivalent to this drawing that I showed you earlier. So cis and trans decalin, very, very interesting structures. They are examples of fused bicyclics because unlike the spirocyclics in which one carbon is common to both rings, in fused bicyclics there are two carbon atoms, the two that I am bold facing, which are common to both rings. Cis-decalin and trans-decalin. Well, I told you a moment ago that there's actually 3 different types of bicyclics, and the type that we've yet to discuss are the so-called bridged bicyclics. Unlike the spirocyclics in which we share one carbon atom, or the fused bicyclics in which we share 2 carbon atoms, in a bridged bicyclic we share 3 or more carbon atoms. 3 or more carbon atoms are shared. Now, how is this possible? Well, it turns out that these bridged bicyclics are quite common in nature, quite common in organic chemistry. Let me give you one example. Look at this strange looking molecule. This is supposed to show that the carbon atoms and the bonds, which I'm bold facing now, are in the front, and these are in the back. And you can see that that carbon right there is common to all the rings, and so is that carbon. We refer to those, once again, as the bridge head carbons. One there, and one there. Now, in this particular case, when I say bridge head, I really want you to focus on the bridge part of that term, because the way you can think about these compounds is that between this bridgehead carbon and that bridgehead carbon, there are these other carbons, and they are essentially bridges which link the bridgehead carbons. You can see between here and there, moving in this direction, that's a 2-carbon bridge. Moving in this direction, that's also a 1,2 carbon bridge, and even moving up here, a 1,2 carbon bridge. So this is a bridged bicyclic in which there are 3 equivalent 2-carbon bridges. It's also possible to draw very different bridged bicyclic systems. I've highlighted once again the bridge head carbons because those are the 2 carbons that are common to all the rings. Well, let's look at all the different pathways. When we move in this direction, there's a 1, 2, 3, 4 carbon bridge which links the 2 bridgehead carbons. So the length of the bridge, not counting the bridgehead carbons themselves, is 1, 2, 3, 4. Over here, in this direction, the length of the bridge, which connects the 2 bridgehead carbons, is 1, 2. And finally, moving up here in this direction, the length of the bridge, which connects the 2 bridgehead carbons, is only 1 carbon atom. That's another example of a bridged bicyclic system. So we've seen spirocyclics, fused bicyclics, and bridged bicyclics. Let's talk about how to name these things. And I'm actually going to work in reverse order now. When we name a bridged bicyclic system, like either of these 2 right here, we're going to name it according to the same sort of idea we were just discussing by focusing entirely on the length of the bridges that connect the bridgehead carbons. We start the name with bicyclo. So that tells us that we're talking about a bicyclic compound. And we're going to put in brackets the lengths of the bridges that are connecting the bridgehead carbons. We always start with the longest bridge first, followed by the second longest, followed by the shortest. The length of the bridge, not counting the bridgehead carbons, is 4 here. So in brackets we write 4.2.1. This is a bicyclo 4-2-1 system, which tells us that we've got these bridgehead carbons with 4 carbons, 2 carbons, and a 1 carbon bridge. To finish the name, we simply refer to the base alkane that has the same number of carbon atoms. Well, if I have a 4 carbon bridge and a 2 carbon bridge and a 1 carbon bridge, that adds up to 7, plus the 8th and the 9th carbon are the bridgehead carbons themselves, 9. Or we could just count 2, 4, 6, 8, 9. There's 9 carbons there. The 9 carbon alkane would simply be a nonane. So this is a bicyclo 4-2-1 nonane. If I go over to this compound over here, which I started with earlier, we can see that there's 2, 4, 6, 8 carbons here, a total of 8 carbons. So this one is going to be named as an octane. Hopefully I gave myself enough room here. It's a bicyclo. In brackets, I need to give the lengths of the bridges, starting with the longest, going to the second longest, and then the shortest. But it turns out that all 3 bridges are the same size. 2 carbon bridge, 2 carbon bridge, 2 carbon bridge. So this is a bicyclo 2.2.2 octane. Bicyclo 2.2.2 octane. Bicyclo 4.2.1 nonane. Let me give you another one. This one's really long. So I've got a bridgehead carbon here and a bridgehead carbon there. This is supposed to be, you know what, it doesn't look like an extra carbon, so I'm going to just make it a 2 carbon bridge. So this is a 1-2 carbon bridge, this is a 1-2-3 carbon bridge, and this is a 1-2-3-4 carbon bridge. So this one's going to be a bicyclo. Start with the longest bridge first, 1, 2, 3, 4. Next longest, 3, 2. Bicyclo 4-3-2. Now we got to figure out how many total atoms are in this, how many total carbon atoms are in this, and name it as the corresponding base alkane. So 2, 4, 6, 8, 10, 11. Another way to get at that is simply to add up these numbers. 4 plus 3 is 7, plus 2 is 9, and don't forget to add in the 2 bridgehead carbons. That gives us 11. So we've got 11 carbons, and undecane is the 11 carbon alkane, so this is a undecane. Bicyclo 4-3-2 undecane. Very, very interesting compounds. Well, what about those fused bicyclics? Can we name those in the same way? Sure. Let's go back to Decalan. This was cis-Decalan, and if you call this cis-Decalan, everybody will know exactly what you mean, and there's no problem just referring to this as cis-Decalan, but it is possible to also name it in the manner we just discussed. So I'll write here, or it's a fused bicyclic. There are the 2 bridgehead carbons. We would call this a bicyclo, and then in brackets we give the lengths of the chains, and so I should say the lengths of the bridges. The longest first, 4 carbon and 4 carbon, that's a tie. So we would call it a 4-4. Don't forget the shortest bridge, which is right there. There's no carbons separating the bridgehead carbons in a fused bicyclic, because in a fused bicyclic they share 2 carbon atoms, and those 2 carbons will be bound to each other. So in a fused bicyclic, the last number is always 0. 4, 4, 0. 0 carbons separating the bridgeheads there. And then we count up the total number of carbons, 2, 4, 6, 8, 10. This would be a decane, which is how we got the word Decalan to begin with. bicyclo 4,4,0-decane, and we do want to indicate it is a cis structure, so there it is. Cis bicyclo 4,4,0-decane. What about some of those other fused bicyclics? Here's one more example. This happens to be a 5-membered ring fused to a 4-membered ring, and once again I'm showing a cis junction. So this is going to be a cis bicyclo. Now the longest bridge is 3, followed by the next longest, which is 2. And in a fused system, the shortest bridge is always 0 atoms between those two bridgehead carbons. My bridgehead carbons are bold-faced now. Total number of carbon atoms, 5, 6, 7. Only 7, so this is just a heptane. Cis bicyclo 3,2,0 heptane. So that gives you an idea of how to name these bicyclic compounds, and you should know how to name them. They're important compounds. And that also goes a long way towards wrapping up everything we need to do with regards to this particular chapter on ring compounds. The last subject I'm going to cover really has more to do with material science than it does organic chemistry, although it's clearly at the border between organic chemistry and material science. I'm not going to test you on this, but I do want you to know that these compounds exist. Polycyclics are the compounds I'm talking about, and polycyclics means not just bicyclic, not just 2 rings, but many, many rings tethered together in special ways. Polycyclics are important species in material science, and they include 2 compounds that I'm going to talk about right now. Diamond, probably heard of that, and carbon sub 60 or C60, also known as Buckminster fullerene or fullerene. Let's look at diamond first. It turns out we've been drawing small pieces of diamond already. Cyclohexane itself maps directly onto diamond. You see, what diamond is an allotrope of carbon. This term allotrope means it's made up entirely of carbon. And for diamond, the type of carbon atom that it's made up of is sp3 hybridized. So if we had a cyclohexane like this, and we simply connected it only to other carbon atoms, we would be on our way to a diamond structure. Here, I've drawn all the axial bonds up, as I should, off of these 3 positions, and then I've connected them to a new carbon atom, and you can see this is kind of a tricyclic type structure. I can do the same thing with the axial bonds that are down, connect them, and now I've got a multicyclic compound, and I can just keep going. If I, for example, start thinking about the various decalins, like transdecalin, I can keep growing this structure. This is now a 3-dimensional structure composed of fused cyclohexanes that are not attached to hydrogen or oxygen or anything else. They're only attached to other carbon atoms, and this thing quickly grows in 3-dimensional fashion, and that is diamond. By the way, that first structure I drew as I was on my way to diamond, this one right here, this is a special molecule all by itself. It's not diamond. It maps directly onto diamond. It's a small piece of diamond. It's called adamantane. Adamantane holds a very special place in the history of organic chemistry, and maybe I'll tell you about that a little bit later. Diamond is a polycyclic aromatic hydrocarbon made up entirely of cyclohexane rings which are fused together in 3 dimensions. Now let's talk about C60. C60, or Buckminster fullerene, what a strange name that is. Buckminster fullerene. The molecule was named after an architect named Buckminster Fuller, who was famous for creating geodesic domes. And the reason the molecule is named after him is because this molecule looks a lot like a geodesic dome. But I'll tell you what it really looks like, and what you'll recognize it looks like, is a soccer ball. So if you look carefully at a soccer ball, there are 5-membered rings and 6-membered rings on a soccer ball. But no two 5-membered rings share an edge. In other words, 5-membered rings are completely surrounded by 6-membered rings. That's what a soccer ball looks like. The next 5-membered ring would be here, and here, and here, and there, and there. And then these would be tied together further by 6-membered rings. And we can work our way around this soccer ball in exactly this fashion. This would be a 3-dimensional spherical shape. This is a curved molecule, curves around in itself, just like a soccer ball does. What's interesting is that all of the carbon atoms in this C60 compound, or Buckminster fullerene, are sp2 hybridized. They're all alkene carbons. And that pi bonds never exist at the juncture of a 6-membered ring and a 5-membered ring. The pi bonds only exist in these positions. You see, if you look at any 5-membered rings, the pi bonds radiate away from them, so that it is a 6-membered ring that has the 3 pi bonds. And if you just follow that pattern, if you continue, 1, 2, 3, 4, 5, if you continue to follow that pattern, then you will have a perfect model for Buckminster fullerene. And again, it's hard to draw this, almost impossible to draw this completely, because it wraps around on itself, and quite a few of those atoms are on the back side of this structure. But it's a spherical structure, buckyball, that has really important and exciting properties. Because of the curved nature of this molecule, all of those pi bonds are slightly distorted. Remember, those p orbitals have to be parallel to one another in order to form a strong pi bond, and if you have one p orbital which distorts a little bit, it's a weaker pi bond that you get. As a result, the pi bonds on these molecules are a little bit weaker than they are on a normal